Hello there. This video is all about inverse functions, which can be kind of a tricky topic at first, but once you realize that it's all about switching your inputs and your outputs, it starts to become a little bit easier. So we're going to go through a variety of different examples involving inverse functions. So let's start first of all with what's happening here. So these examples go by relatively quickly. So we've got 3 examples at the level 1 level and then 2 at the level 2 level as we're talking about all the different ways that we can approach inverses of functions. So a quick little introduction. This is basically our definition of what an inverse is. And it says is if f and g are functions, then g is the inverse function of f if f of g of x is equal to x and g of f of x is equal to x. In other words, when you plug x into g and you plug that into f, you end up where you started. So x is where you started, you plugged it into g, you plug that into f, and you end up back at x. So same if we plug x into f and then plug that into g, we also end up back at x. So that's kind of our definition of what an inverse is. We write g with the notation f inverse, so that's kind of like f to the negative 1. A lot of people get confused, but this is not the reciprocal 1 over f of x. So we're going to have to make sure our notation is distinguished here. But the idea is that the f inverse is written with this superscript negative 1. So one thing that we'll notice is that I mentioned that with an inverse, we're going to switch our inputs and our outputs. Well, what that really means is that the domain of f is equal to the range of f inverse and vice versa. And that'll play a key role in helping us to understand what the inverse function is doing. So a quick little introduction. The inverse is a reflection of the graph of f across the line y is equal to x. All right. And a function f has an inverse also f inverse if and only if each horizontal line intersects the graph of the function in at most one point. So let's start with the second thing first. We'll see the first thing in just a minute. So what I did was I created this little Desmos slide right here, which showed a horizontal line. And if that horizontal line intersects the function at most one point, then we know that we have an inverse. You'll see that it sounds familiar, and that's because this is very much related to our idea of the vertical line test. Vertical line test told us that if a vertical line could only intersect the function in at most one point, because that told us that each x has at most one y value. Well, in this case, to be an inverse, each y must have at most one x value. So it's the reverse, right? And a horizontal line will help tell us whether or not the y intersects the graph in more than one point. If so, the function is not an inverse. If we intersect it at most one point, we know that we have an inverse. So then we're going to tackle this second point in just a minute. The inverse is a reflection of the graph of f across the line y equals x. So hold on to that thought. So first of all, apply the horizontal line test to determine whether its inverse function exists. So you'll notice in A, I've got this absolute value function. It's possible to find horizontal lines that intersect the graph of f of x more than once. So for example, at y is equal to 2, we can draw ourselves a horizontal line that intersects the graph more than once. Now, one of the things that we'll talk about in class is that if we restrict the domain to something like, for example, 1 to infinity with 1 included, we would only get the right half of this absolute value function. Or we could restrict to the left half, negative infinity to 1. And in those cases, we're eliminating the parts of this function that would cause us to not pass the horizontal line test. So then f would have an inverse. But as it stands right now, no inverse. What about this second one here? What's going on with this? Well, the second one does pass the horizontal line test. Whenever we draw a horizontal line, it intersects the graph in at most one point. So this function g of x would have an inverse. Okay, now let's get back to this idea of a function's inverse being a reflection across the line y is equal to x. So in this case, I give you a graph, f of x in red, and we want to try to graph f inverse of x. Well, if you have a graph and some points on the graph, it's actually pretty easy to do because all you're doing when you're graphing an inverse is you're graphing the points with x and y switched. So for example, I've got 2, 7 right here. Well, on the inverse, that point will become 7, 2. We've got 1, 0. That point will become 0, 1. And then we switch x and y on this purple point. It becomes negative 1, 0. And on the green point, it becomes negative 9, negative 2. So when I go to graph, notice that all my points are reflected across this line y is equal to x. And so we get our inverse right here in black because I've switched all my x's and my y's. So it looks like it's reflected. That's what happened with it. Okay, so that's another idea to keep in mind with our inverses. Finally, for our level ones, how do we find inverse functions? If we're given a function, is it possible to figure out what the inverse function is? Well, of course, the answer is yes. If we switch our x and y and try to solve for y, we're going to be able to solve for our inverse. So in this case, y was equal to 2 times the square root of x plus 6. If I switch my x and my y, I would get x is equal to 2 times the square root of y plus 6. That's what we do with inverses, switch our inputs and our outputs. And then step 2 is to try to solve for y. So I isolate the y by dividing by 2 on both sides. And then I want to square both sides because I want to get the y out of the square root. So I get x over 2 squared is equal to y plus 6. Now I simplify a little bit. So I get x squared over 4, and then I subtract 6 on both sides, and I get y is equal to x squared over 4 minus 6. And this is true whenever x is bigger than or equal to 0. And the question is, what in the world is with that? X is bigger than or equal to 0. Well, if you remember what the square root function looks like, it has a range of y bigger than or equal to 0, unless it's been shifted or something. So in this case, what happens is, if y is bigger than or equal to 0 for the function, x has to be bigger than or equal to for our inverse. Right? So the domain and range will switch. We'll talk about that a little bit more in class. One last thing you'll want to do when you deal with inverse functions is to verify. So remember I said that when you plug the inverse function into the regular function, you should end up with x, because you end up with where you started. So in this case, if I were to take f, which is 2 times the square root of x plus 6, and plug in my new inverse, x squared over 4 minus 6, in for x, you'll notice that a lot of things reduce. So I got x squared over 4 minus 6 plus 6 inside my square root. And when I cancel out 6 minus 6 and the plus 6, I end up with the square root of x squared over 4. And then when I reduce this down, this becomes x over 2 times 2, which is just x. That's what we want to see. When we plug in one of the functions into the inverse or vice versa, we end up back at x. And then the same thing with f inverse of f of x. If I plug f of x, which is that 2 squared root of x plus 6, into my inverse, I should see that I end up with x. Well, notice what happens when I square my numerator here. I get 4 times x plus 6 divided by 4. This reduces to x plus 6 minus 6, which is just x. So we can verify that we have an inverse by plugging our inverse into our function and vice versa. Okay, now for a couple of the more advanced problems, the level 2s. So let's say Joey earns $10 an hour, works at least 40 hours per week, and gets overtime pay 1.5 times his regular hourly rate for any time over 40 hours. And I'm going to go ahead and give you the function. So his total earnings can be given by the function 400, which by the way is 40 hours times $10 an hour, plus $15 an hour for every hour over 40. One way of writing that is x minus 40 here. And x is just going to stand for the number of hours that he worked per week. So what is the inverse function f inverse, and what does it mean in this problem? So it's helpful to remember that f of x is just the function which will tell us how much Joey earned by knowing how many hours he worked per week. And we have to adjust this function because he's going to get a different pay for the number of hours that are bigger than 40. All right. So what does the inverse mean? Well, let's find the inverse first. Remember, we're going to switch our x and our y, and f of x is our y in this case. So when I switch my x and my y, I get x is equal to 400 plus 15 times y minus 40. And I want to isolate the x, so I subtract 400 and divide by 15. And then I'll add 40 to both sides, and I get this inverse, which is 40 plus x minus 400 over 15. So that's our inverse. I solve for y in this case. Well, what does this mean? Well, remember I said that the function means if I knew the number of hours, I would know how much Joey earned. Well, reverse it. That's what the inverse does. So if I know how much he earned, we could determine how many hours he worked. So for example, if x in this case was equal to 460, I could plug that into this function and solve, and I would get f inverse of 460 would be 44 hours. Okay, so It's the reverse. If we know money, then we can figure out number of hours worked. All right, finally, we're going to start talking about tables and how to actually do inverses and other sort of things with tables. So we are given a function right here, all right, x and f of x. So the x values are given for certain x values, and so are the function values. We want to first determine if the inverse exists for this function above. Just for these values, there's nothing that we know of in between them. And if so, complete a table for f inverse. So first step, does f inverse exist? Well, we need to look at our y values. If we have repeat y values, there's going to be no inverse, just like with the horizontal line test. And we look through and we see no repeats. So what we need to do is create a table of values for f inverse. So you notice what we're going to do with an inverse is we're going to make our function our input and we make our x's our output. So for example, right over here, I see that f of 2 is equal to 1. So that means f inverse of 1 is equal to 2. This should say f inverse right here. I can go through and I can do the same thing when I notice that when my function is equal to 2, my x is equal to -1. So we would say for our inverse, f inverse of 2 equals -1. We're just switching our inputs and our outputs. And we can do the same at 7, -3, 8, -2, switching inputs and outputs, 10, 0, and 12, 1. And so we've created a table of values for f inverse. So in summary, the inverse function is obtained from switching inputs and outputs, very useful for undoing the operation of a function. And as with other function topics, the inverse is tied to our graphical and tabular representations. We'll see you on the next video.